Tell me now, big man.
Come and sit down here.
Maybe it's not our camera.
Yeah.
Okay.
So, don't be too like. Let's worry that I should know last time. We know, you know this from
Okay, look at this, look at this, look at this. So we said that series has to do with sum of terms. Sequence simply means a set of the terms. We are putting all the terms together, just listing out the terms. That's what a sequence is. So in the case of a sequence, we represent it as a sub n. Okay, you can write from n equal to 1 or whatever n you are starting from to infinity. Okay, so this is just a sequence of terms. You are starting from n equal to 1. You can as well start from n equal to 0. You can start from n equal to 10, depending on the sequence you are given. So this takes on natural numbers, okay, from that particular value to infinity. So you can have a1. So this sequence simply means you list a1, a2, a3, and so on and so forth. Okay. Whereas in the case of series, you will have it as a summation, because indeed it is a summation of the terms you have here. So the sum of the terms of a sequence is what makes a series. So in this case, this is simply going to be from n equal to 1 or whatever n to infinity. So series is a summation. So this means that you have this to be a1 plus a2 plus and so on and so forth plus, this continues like that till infinity. You are taking the sum of all the terms. Okay. So when we talk about the convergence of a sequence, we are simply saying that what happens as n becomes very, very large. Can we say that the terms of this sequence will approach a certain value? Okay. If we can get the exact value, that is, if we take the limits of a sub n, you can call it x sub n also, as n approaches infinity, and we find it to be some l, which is a real number, okay, then we say that what? We say that a sub n is convergence. Does that make sense? A sub n is convergent. So if there is no such limit, or that is in the limit, for instance, is infinity or minus infinity, that means the series and the sequence is not convergent. So for you to get the convergence of a sequence, you simply take the limits of the n term of the sequence as n approaches infinity. If the limit exists, yes, the sequence is convergent. Does that make sense to you? Alright, so that means that in this case, for instance, if you have the series sequence 1 over n from n equal to 1 to infinity, you may be asked if this is convergent. That means you just want to find out the limit of 1 over n as n approaches infinity. What's the limit of 1 over n as n approaches infinity? That is 0. Abi? 1 over infinity, which is 0. So obviously, this is a real number. So it means that this series actually converges to 0. Is that clear? Sorry, this sequence actually converges to 0. Does it make sense? Right. In the case of our series, we are saying that can you actually get the sum to infinity? Are we together? That means can you sum all the terms you can have for that series and get a real number from it? That is, by the time you are taking the sums from beginning to infinity, there's nothing like an end here. If you want to take the sum from beginning to infinity, will it actually give you a real number, or it's going to become extremely large, or it's going to become extremely small? So if it's going to give you a real number, then we say that the series is convergent. So in the case of convergence of a series, we are not really interested in a sub n, rather we are interested in the limits of s sub n as n approaches infinity. If this limit is going to give us some L, which is a real number, we say that the series is convergent. How did we come about S sub n? S sub n is simply the sum of, or the partial sum of the terms of the series. Okay? That means the sum of the first n terms. So if you have a formula for the sum of the first n terms, and we take its limit as n approaches infinity, and you get it to be a real number, that means that series is convergent. So we have considered some of them in the past where you can play around with series. But what's actually important here is the fact that when we're talking about series, we want to be able to test for the convergence of that series when you are just given its definition. No, it is not in all cases. Of course, you can be given some series and then examining the pattern, you may be able to come up with the formula S sub n. For instance, we talked about the geometric series the other day, where I told you that if you have a series, let's say you have something like summation a r raised to the power n minus 1 from n equal to 1 to infinity. You are familiar with this, Abi? Okay, this is simply going to be a, okay, and that's the first one will be a r raised to the power 1 minus 1, that's 0. This is going to be a plus ar plus ar squared plus, and so on and so forth. And it continues like that. And in this case, we saw that we could actually get the sum of the first n terms. The sum of the first n terms for a geometric series. Can you remember? We said that this will be a into 1 minus r raised to the power n all over 1 minus r. Does that make sense? Can you remember this? And we say that, so if you want to establish if this series is convergent or not, you can find out if the limit of s of n as n approaches infinity exists. Okay, so we now look at it that, okay, if I want to get the limit of s of n as n approaches infinity, that means I'll be interested in the limit of a into 1 minus r to the power n over 1 minus r as n approaches infinity. So now there's a problem here. As n approaches infinity, whether or not this converges depends on the value of r. Altogether, we are raising r to some infinity. If it's going to be a number, or if it's a number that has its modulus to be less than 1, altogether, by the time you raise it to the power of infinity, it's going to become 0. Do you understand that? Otherwise, it is going to give you infinity. Is it making sense? Okay. If you have this arrow here, if it's a number, if it happens that modulus of r is less than 1, so what's that? For instance, we have 0.5 and you raise it to infinity. 0.5 times 0.5 times 0.5, continue multiplying by 0.5, it is going to approach 0. Does that make sense to you? So as n approaches infinity, r raised to the power n approaches infinity, provided that the modulus of r is less than 1. Is it making sense to you? Alright, so if the modulus of r is less than 1, we say if modulus of r is less than 1, then we conclude that the s to this sum to infinity is going to approach a over 1 minus r, okay, as n approaches infinity. Do you understand that? Why? Because this will become 0. If this becomes 0, this is going to be a times 1, that's a, divided by 1 minus r. And this was what we were told. We were told that this is actually sum to infinity of a GP. Okay, and you usually find this when the modulus of r is less than 1. So it's feasible this way to just examine the behavior of the series and tell whether or not it will converge. Okay, but usually we want to test just by using a sub n. So if I just given a sub n, we want to be able to reach some conclusion about whether or not the series is convergent. That's why we talk about the test of convergence. Are we together? So how do you test for convergence of a series? So in the case of a sequence, it's quite straightforward. You just get the limit of the an as n approaches infinity. Okay, so when it comes to convergence of a series, okay, using its own an, the first thing you want to check is that the limit of an as n approaches infinity must be 0. Do you understand me? Okay, that means that for convergence of a series, any kind of series you are given now, for convergence of a series, summation a sub n equal to whatever, to infinity, okay, it is necessary, okay, but not sufficient, necessary but not sufficient that the limit of a sub n as n approaches infinity be 0. Okay? So the first thing you want to check if the limit of a sub n as n approaches infinity is 0. If it is not 0, that means the series is divergent. There's no other thing to check. You understand me?
Yeah.
You get that? But if it is 0, we cannot conclude because we said that it was a necessary condition but not sufficient. Is that clear? That means that for a series to be convergent, limit of a sub n as n approaches infinity has to be 0. All together. But it can also be 0 and not converge. So we will have to do another test to actually confirm if it is convergent or not. But once you check the limit as n approaches infinity and it is not 0, there is no other thing to check. Just move on. It is not convergent. Is that clear? Is this clear? Alright. So there are some cases. That means that there are some cases where you can have the limit to be 0, yet the series is not convergent. Okay? One of such, which is a very common example, is the series 1 over n from n equal to 1 to infinity. Okay, which is usually called a P series with n equal to 1, and with p equal to 1 rather, is actually not convergent, even though the limit of 1 over n as n approaches infinity equal to 0. You get that? To say it's a necessary condition, but it is not sufficient condition to conclude that the series is convergent. So we have some tests to please. Who has the Google Classroom? Please open it. So we have some tests to carry out under different conditions. So let's quickly write out those tests. Okay, this is iPhone. Yeah? It's like I don't know how to operate this Android. So look at this now. Look at something, please. Look at something. So we have different kinds of tests. So just write them down. We have what we call the comparison test. Comparison test. That means we want to compare two different series. Okay, and then so that's where this should start. Yeah, comparison test. So just write down this condition. I'm trying to summarize. Look at something now. If x sub n is less than y sub n for all n greater than some n naught, okay, we say that the series x sub n converges if y sub n converges. And the series y sub n equal to 1 to infinity diverges if x sub n diverges. So to do a comparison test, please pay attention to this. Please pay attention, pay attention, pay attention, pay attention. Here, look at something, please. to do a comparison test, you will usually make use of two fundamental results. Okay, it's the idea of geometric series and P series. So we know that a geometric series will always be in this form, a r raised to the power n minus 1. You know, this may not be n minus 1. It could be n, it could be maybe n plus 1, it could be n plus 2, n minus 2. Do you understand me? So far you are increasing this, okay, with subsequent terms. You are increasing the power with subsequent terms. Then we will say that when you have anything like this from n equals to infinity, this is convergence. Is convergent when the modulus of r is less than 1. So that's one thing you must know. And then another one is the P series. The P series is generally defined as 1 over n raised to the power p from n equal to 1 to infinity. It's convergent. The P series is convergent when p is greater than 1. So those are the two things you need to know here. So what we do in comparison series is that we are given a series, then we try to find another series that is convergent, that we know is convergent or we know is divergent. Then we will try to compare it with this one. We'll compare its value with this other one. We want to establish its convergence. So if you are able to satisfy any of these conditions, then we can conclude for that particular series its convergence or divergence, as the case may be. So let's see an example on that. Look at this series. You want to test for the convergence of this series. 1 over n into n plus 1 is from n equal to 1 to infinity. Just pay attention to this now. Pay attention. So you know that this is the same thing as having the series from n equal to 1 to infinity of 1 over n squared plus n. Are we together? We do know that 1 over n squared plus n is always going to be less than 1 over n squared. Do you agree with that? Do you understand that? Right, because once we are decreasing the denominator, we are going to have a higher value. You know, this is always positive. This is a natural number. Do you get me? N represents a natural number which goes from 1 upward. So this is always going to be greater than this. Does that make sense to you? Yeah. So the idea is that means if I consider this as a series and I consider this as a series, what can I say about both of them? Can I tell already the property of this series? I mean, can I tell its convergence, whether the series is actually convergent or not? So in this case, I have 1 over n squared. From this, you know, 1 over n squared is a P series, Abi, with P equal to 2. Does that make sense? So P is equal to 2, that means P is greater than 1. That means this is a convergent series. Is that clear? And now we are saying that the terms of this series are always less than this. Is it clear? So if this is always less than this, and this one is convergent, then definitely this is also convergent. Does that make sense? Does that make sense to you? So that's the idea we have expressed here, that if yn is always greater than xn, and we establish that yn converges, that is, if yn converges, then xn also converges. Do you get the idea? Do you understand the idea? Right. And then if it is the other way around, if it happens that yn diverges, if it happens that xn diverges, then we also conclude that yn diverges. So the idea is that look at something. You know, the idea with divergence, please pay attention to this. The idea with divergence is that we're saying that this thing here, 1 over n squared, when you start from 1 plus 1 plus 1 over 1 plus 1 over 2 plus 1 over 3 plus, and so on and so forth. You can sum all of these things together from beginning to the end and get some real number L. Is that clear? Now, we are now saying that this one, no matter the term, at every point, this one is always going to be less than this. Are we together? Do you understand me? For instance, when n equal to 1, this is 1 over 2. When n equal to 2, this is going to be 1 over 5. So since this one is always greater than this, and this one is going to give me a real number, there's no way this one can give me infinity. Do you get me? Because every term of it is always less than this one. Is it clear? Is this clear? That's why we're saying that. So if this converges, then this one has no option. It also has to converge. Is that clear? And now, in the same manner, if we are comparing the other way around, if I knew that this diverged, that means that something that is lower than u actually will sum to infinity. Then you that are greater, you will definitely also sum to infinity. There's no option. Do you get the idea? So that's the idea with comparison. So that is that about that. So you just always have this in mind. So you can always, in most cases, you'll be able to reduce it to a P series and do a comparison, or you'll be able to notice if it's a geometric series or it's comparable to a geometric series and do a comparison also. So that is that about comparison test. Then we talk about another one, which is the ratio test. So the next one is integral test. So let's talk about integral test. Let's just write each of them down. Then I'll tell you when it's appropriate to use each of them. Okay, when you want to use each of these tests. Look at something now. Integral test says that if you take the integral from some point b, okay, to infinity of f of t dt, and now you get this integral to converge. If it converges, that means it gives you some real number. All together, where do we get f of t? You simply get it from your a sub n, the definition of the series. So if you take that definition as some integral, please pay attention, as some function. For instance, this is 1 over n into n plus 1. If I took it as a function that depends on t, then I'm going to have something like f of t is equal to 1 over t into t plus 1. Does that make sense? Then I'll take its integral with respect to t. So, I'll take the integral of this with respect to t. So I'll say integral of 1 over t into t plus 1. Is that clear? Then, when I take this integral with respect to t, you may be able to find the integral, okay, by just simplifying. So if it's a simple integral that you can easily get, yes, this method is fine. But if it's not an integral that you can easily obtain, then you might want to check out other methods. But this is just saying that when you now take this integral from any arbitrary point b now to infinity altogether, you should get a real number. So if you get a real number, then the series is convergent altogether. If you don't get a real number, maybe the series does not, maybe the integral does not exist. That means you cannot compute. But if the integral is infinity or minus infinity, that means the series is divergent. Does that make sense? Do you understand the idea? Alright, so that's what we call the integral test. So integral test is usable to come in handy when you have a function that you can easily integrate. Is that clear? Easily integrate is relative to you. If you know how to integrate it easily, it's fine. And of course, there are some functions that you cannot integrate. Of course, that's why we talk about numerical method. That when you have functions that you cannot integrate, then you need to use numerical method. But that's not applicable here. You can't use numerical method from a number to infinity. Okay? So you can't say that you want to solve this, for instance. Let's say you're starting from 1 and then you go into infinity and you want to use that method. It's not possible, right? I'm just going to stay there from morning to night. Alright, so that's that about integral test. Then we also talk about the ratio test. So look at ratio test. Ratio test. The ratio test, we call it the integral test. So I said that if this is going to give you a real number, then it's convergent. Altogether, if it gives you infinity or minus infinity, it is divergent. Okay, if it doesn't exist, it is inconclusive. That means you cannot conclude. You have to use something else. Okay. So then the next one is ratio test. So for ratio test, you have to find out the limit as n approaches infinity of an plus 1 all over an. Okay, modulus. So if this is going to give you some L, please pay attention now. Pay attention, yeah. Okay.
Students get it big.
Cheese. We get me two for this thing. Yeah, that formation, you guys don't spoil it. That formation will spoil for CP University.
So in this case, you're going to get some value for this, okay, a real number. But now we now say that if L is less than 1, okay, then the series is convergent. Okay? And otherwise, the series is divergent. Does that make sense? If you get a series, if you get that result to be less than 1, the series is convergent. No, if L is not a natural number, that means you cannot use that to conclude. Is that clear? So if you have L to be less than 1, it is convergent. That's absolutely convergent. If it is greater than 1, it is divergent. It's a real number, but it's greater than 1. Okay, that can also be infinity. Okay. No. L can be anything actually. If it is less than 1, minus infinity is less than 1. You get that? Yeah, it is convergent. If it is greater than 1, it is divergent. Does that make sense? And if L is equal to 1, that means you cannot conclude. The test fails. Is that clear? Where is ratio test appropriate? Please pay attention, pay attention. If you want to do ratio test, that means maybe you are given an expression that contains, I've told you before, a factorial. Maybe you have n factorial. Now when you have n factorial, maybe you want to, you now do n plus 1 factorial over n factorial. You know they can easily cancel out.
Yes.
You can't do integral of factorial, Abi? Do you understand what I just said now?
Yes.
So most of the other cases may not work for factorial. And then also when you have something raised to the power of n, let's say you have a number raised to the power of n. You know, if you raise to the power of n plus 1, you can easily divide by its raised to the power n. They will easily cancel out. Does it make sense?
Yes, sir.
That's where ratio test is good. And then that's that about that. Let's talk about another one. We have the Rehab's test. So Rehab's test is usually good when you have this kind of case and then you have used the ratio test and the ratio test fails. If the ratio test fails, then you can use the Rehab's test. Okay? So Rehab's test is quite similar to this.
Tomorrow is testing.
Tomorrow is ratio test.
You never read anything now.
So look at Rehab's test. It says that when you get the limit as n approaches infinity of n into 1 minus modulus of an plus 1 over an, and then you get it to be L. So in this case now you are multiplying by n and you are subtracting it from 1 and multiplying that result by n. Okay? So it helps you if this test fails, you can consult the Rehab's test to see if it's going to work for your situation. So it converges. So the conditions for this are opposite of the one for ratio test. That means in this case, if L is greater than 1, it is convergent. If L is less than 1, it is divergent. If L is equal to 1, in this case also, it fails. That means that, yes, for both of them. So in this case, if L is greater than 1, it's what? It's convergent. So say it is convergent. And then if L is less than 1, it is what? It is divergent. Okay, if L is equal to 1,